How Unix time works, the Epoch explained. Keeping time, layer 3, representation. Time is a stack, not a number. Here's the whole time stack. Oscillator at the bottom, distributed time at the top. Layers 0 through 2 got us the kernel's notion of now. Now we have to write that moment down as a number. That's our layer today, layer 3 representation. The Epoch, time T, ISO 8601, and the famous Y238 problem all live right here. There's no year here, no month, no zone. It's just a running tally of seconds. One tick, one tick, one tick. 1,700 million and counting. Every count needs a zero. Unix times 0 is midnight, January 1st, 1970 UTC, one fixed instant the whole world agreed to count from. Take the raw count and divide by 86,400, the number of seconds in a day. You get 19,675 whole days, with 80,000 seconds left over. Walk those days forward from 1970 and you land on November 14th, 2023. Carry the leftover seconds into hours, minutes, and seconds. 2023, November 14, 2213, 20 UTC. It's pure arithmetic. The library does it for you, but there's no magic in it. This is the part people get wrong. The stored number is UTC, full stop. New York and Tokyo aren't different timestamps. They're the same number, displayed through a time zone lens that gets applied later, up at layer 6. You can go either direction. Local time and GIME turn the count into a calendar to display it. MK time and time GM turn a calendar back into a count to store it. The count is the source of truth. The calendar is just a rendering of it. When a human or an API needs to read it, the count becomes a standard string. The T splits date from time, and that trailing Z is the whole ballgame. It pins the string to UTC. ISO 8601. We dedicate episode 03-03 to getting this format exactly right. Same instant, 2 units. C and POSIX time T count seconds. JavaScript's Date.now and Java's current time millis count milliseconds. Feed one into code expecting the other, and your timestamp lands either back in 1970 or out in the year 56,000. Always know your unit. Here's a subtle truth worth slowing down for. Unix time assumes every single day is exactly 86,400 seconds. Always. No exceptions. But real UTC occasionally inserts a leap second, a literal 235960 tick. Unix time just doesn't count it. So a Unix timestamp tracks UTC, not the continuous atomic scale TI. A known wart will fully unpack at layer 6. Time T is a signed integer. A signed 32-bit count tops out at 2,147,483,647 seconds, which is 031407 UTC on January 19, 2038. Add one more second. The odometer rolls. The sign bit flips to 1. The count goes hugely negative, and the date snaps to December 13, 1901. Suddenly it's the wrong century. That's the year 2038 problem, Y2K, but in binary. The fix is boring and total. Use a 64-bit signed count. That moves the wall out about 292 billion years, past the age of the universe. Modern systems already did this. The danger lives in old 32-bit binaries, embedded gear, and file formats that still bake in 32 bits. So a timestamp is a count, not a date, and it's UTC. But is the count actually correct? That's layer 4. Next up, NTP keeps it true. See you in playlist 04. Keeping time. Time is a stack, not a number.